And so what we're going to do again here is cover the core training session. And I'm going to do a quick recap of AllJoyn. And so AllJoyn, again, is an open source framework that's really designed to be the glue for the Internet of Everything. And what it allows for is the ability for devices and applications to publish a set of APIs on the local network in a standard way. And this is what everyone understands as software developers. We understand how to interact with APIs, we understand how to call methods, we understand how to set up listeners, and as such it yields to a very friendly framework. And so you can really consider these APIs and what we're going to be talking about them later on and throughout the presentation as interfaces. And these interfaces are composed of the functionality that you want to define and how it's going to be defined. And AllJoyn provides that whole mechanism on a chipset agnostic way, on a radio agnostic way in which to publish that set of interfaces and publish to all the nearby applications. Here is how you can interact with me. So AllJoyn does all this by setting up a distributed bus architecture. And it really is what enables everything to function. And AllJoyn passes messages back and forth. So the protocol is based in a clean room environment rewritten from the dbus protocol spec, but it's evolved much more than the dbus wire protocol. It has off-device capabilities, so advertising and discovery, there's security built into it. There's all of these different transports that can happen over Wi-Fi direct, over Bluetooth, over Ethernet, over any IP transport. And all these things allow AllJoyn to function and interact and interoperate with everything else because everything sends AllJoyn messages. And the way that these AllJoyn messages are sent are really considered the core of the software as a routing node, right? This is something that receives messages and it passes it up to leaf nodes, which can either be an application or what we call the AllJoyn thin client, which I'll do another overview in a little bit on if you remember from last presentation. And routing nodes can connect to other routing nodes. This is how the bus architecture is formed between the different applications. And you can create this mesh where all the different applications, regardless of the transport of how the routing nodes are connected, can interoperate and communicate with one another. So on the left side of the image here, you can see there's a routing node hanging off by itself. That could maybe be over a Bluetooth connection. And all the way over the devices on the right side of the screen, those two other routing nodes, those may be over Wi-Fi direct. And each of the leaf nodes will be able to discover the presence and be able to interact with everything. And I'd like to remind people, if you can, please go ahead and keep your microphone muted when you first sign in here. And so all of these, so all the routing nodes and everything kind of forms this whole network at which anything can communicate between each other. So the way this happens is we went over in the last training session, which if you weren't present, I would encourage you to go back and listen to the core training 1 because we really focused on these fundamentals, and I'll touch briefly on them as a recap. So there's one side of the application, and your application can do both of these at the same time. But one side's going to say, I have these interfaces, or here is a well-known name that I'm offering up. The other side is going to look for those specific interfaces, and here you see that one application is looking for the org AllSeen Media audio. And it's going to then start to form a connection over that. And over Wi-Fi, what we've done is we've used a UDP multicast in order to set up and discover that presence and perform a handshake. And we got in deep into how that worked last time on the advertising and discovery. And once you're then connected, you have what's called a session. And this session has a unique ID associated to it so that you can route messages to all applications that are part of that session. Really, it's forming a group at a conceptual level. And so once these sessions are maintained, the actual routing nodes persist the connections. And so we're really efficient in how the design is architected such that if there were many different client apps on one device trying to interact, so that image there on the left, trying to interact with everything on the right side over there, that's the service side, it would leverage that one same connection over to the other device, so we're not chewing up extra bandwidth, and we're not really cumbering and bogging down the network or the IP network or the wireless transport that we're using if it's Bluetooth or Wi-Fi direct and so forth. So the way the architecture stack is developed is AllJoyn sits on top of the wireless protocols on a device. So whether you're running on a memory-constrained device where you have your Wi-Fi drivers or your Bluetooth drivers, or you're running in a high-level OS, we leverage that fundamental stack, and we provide an abstraction layer that's part of the framework that really manages the discovery, the management of understanding when devices come and go in the network, the security, how do you encrypt the data that you're sending to another application, and how do you handle connection management. So if the radios, if you discover over one transport, how do you connect up, and how do you maintain and persist that? And then one thing that we've done, and I would encourage you to sign up for next week's presentation, which please check the calendar because the date has moved. It is on Tuesday next week. And what that presentation will be going is it will be diving deep into these service frameworks. Now these are small modules that have built on top of AllJoyn, so they leverage all of the information that you've learned in the last session and in this session to perform meaningful communication. So notifications, for instance, is one way at which we can send really a text message to all the devices. It's a small, short amount of text, and it can have language encoding associated with it, and it would travel to any application that is running the receiving side. So anything that's interested in receiving and displaying a notification can do so. And that functionality, as we've defined it as part of the service frameworks, really promotes interoperability, because if everyone uses this module, everyone can interact because we're all using the same common set of interfaces, in essence APIs. And then you have your application on top of that that you would write that can leverage the framework by itself, or that can leverage these basic services. So of the two sides here, there's the client library, and then there's the router piece of the software. And the client library is the set of APIs that you interact with, right? So these are the calls that you will use at which to avoid having to understand how to set up a TCP connection between devices. How do you do pre-associated discovery with Bluetooth and use Bluetooth profiles? So all this stuff you would use is managed by the router side of it, and you use the high-level APIs with AllJoyn at which to create your objects, create your interfaces, and call those methods on other applications. And so the client library is broken into two parts. There's the standard client, which runs on a high-level OS, like your Android, iOS, your Linux desktop, your Windows desktop. Maybe it's even OpenWRT running on a router or some other piece of software. And then there's your thin client, which is designed for memory-constrained devices. So with both implementations, the standard client is written natively in C++, and it provides multiple language bindings for all the different language platforms. So if on Android you prefer writing up in Dalvik, you can use the Java language binding at which to leverage that interaction. The same is true on iOS. You can either program in C++ or you can write in Objective-C. On the thin client side of things, this is really for these memory-constrained devices, and it does not contain the routing part of the software. So this is dependent, and a device running the thin client software would be a leaf node. So it would need to connect up to an application running on Android, on iOS, or on a Linux platform. And we discussed this in the last presentation through the fundamentals at which the thin client uses to find a routing node is all through discovery of that routing node that is advertising, and then it forms a session to transmit AllJoyn messages across. So the functionality again here is that there are these objects of implementation, and these objects are comprised of interfaces, and those interfaces contain methods, signals, and properties that make it up. So you can really look at this all as basically a exposure of a library across the network, where your interface is really your header file, right? And what everyone else sees, and they can ask you what APIs you support, is through a process called introspection. And that will return all the methods that are exposed and list out in XML Markup Now, interfaces, I want to be clear, are not XML in themselves, but you can define an interface with XML, and we're going to go into that. So once you've connected, there's two sides to the equation here. One side has registered these APIs into separate paths, right? So they have objects that implement the interfaces, and on the other side, you create a proxy object. So you can kind of consider this conceptually as looking in a mirror, right? Where your proxy object is the reflection, and you can reach out to the real piece across the AllJoyn bus and call those methods or start to receive signals from the objects. Right? So it yields very well, and the session ID is an important piece because it allows for flow control, so that messages will route just to a group, or you can execute across each one individually and uniquely address each of the different devices. So it gives you that entire flexibility. So again, a recap. Last week we covered advertising, and this is really how you let other applications know that you're there, and you let them know what services you support. Discovery gives you the ability to find those services, find those applications, and Sessions gives you the ability to connect up in order to start to use the concepts you're learning today on executing bus method calls and sending signals and manipulating bus properties. So again, the sequence of events here, so you can visualize this, is that one side, and you can do this both advertise and discover, it publishes a well-known name, or it advertises, again, a set of APIs that are exposed. Then a join session occurs. There's a callback that executes on your session port listener. This returns back a value of true or false to accept or deny access. That triggers two sets of events where the other side's session port listener will say that it is accepted. On our side, it will say that the session is connected, so session joined, and now we have an ID. And now we have the ability to start to execute and have traffic flow between all the different devices. So objects, again, they represent your API. Method calls are remote procedure calls, and you create what's called a proxy object, and you'll see this in the code. And signals are emitted and sent out to everything on a session ID. Now there's a concept called a Sessionlyst signal, and the software and how today you're going to learn about each of these different components is through a feature called About. And this is that piece that we talked about for service level discovery, and I keep coming back to it. It is a feature that's more in line with the service framework, but it's part of the core software because it gives you the ability to understand what a device make, model, manufacturer, what the application is, what the version number is, any arguments that you choose as a developer to input, and then specifically what interfaces are present and where do they live in the hierarchy of the bus objects. And so these Sessionlyst signals is a shortcut to everything in the last session, so that advertisement, that discovery, that connection, it rolls that all into one piece into the AllJoyn core under the software stack that's there under AllJoyn core router Sessionlyst object.c, or CC, sorry. And so that's where that software lives, and it's really a mini AllJoyn app wrapped up into the routing part of the software here at which to move messages without having you as a developer form these sessions. And it might sound a little complicated, and we'll dive into it at the last part of today's. So looking at things conceptually, again, it's an object-oriented approach here to the implementation. Your interface can be implemented. You can have one interface implemented by many bus objects, and those bus objects can be assigned into different locations of software for physical representation. So you can see here, each of these applications have used an interface, they've implemented it by the bus object, and they've registered it to different player paths. And then once they connect, they'll be able to have each of those objects interacted with remotely. So an interface, again, think of this as your header file of a distributed system. It can be introspected so that you can ask, what is this org AllJoyn about? Right? What is that? And you can get back an XML structure that gives you the representation of it. And that structure is a collection of bus methods, which are the remote procedure calls, signals, which go to all applications in a session, or in that case of a sessionless signal, all applications set to receive it. And a property, which is really a variable that's predetermined by a set of get or set methods, and you can define that in your software when you build the interface. So people then ask, okay, great, I have these set of APIs, but what can I actually send across to the other applications? Am I limited to primitive types? You know, what are the variables that I have to play with? Do I have just strings and I have to figure out how to parse these strings? And the answer is that what we can send across either a bus property can be any primitive type, a signal and bus method, they can represent complex interactions of all these types. So we have strings, integers, shorts, floats and longs, and we have an object path. So we can actually say, here is the entire object of where it lives in its hierarchy, and shoot that across the network. And then we have container types, like arrays that can be defined, and so we can have an array of strings. And these letters that are next to these types that are here, you'll see that throughout the software and when you write your software, because these are the signature values that you set to the types so that AllJoyn knows how to do the data marshalling correctly. So in C++, when you have a char star and you send it over to the other side, it needs to know how to interpret those bytes for a Java application that takes that and sends it up as a Java string. So in order to define an array, all we do is in the signature piece, we give it an A before the primitive type that we are going to build up. We also have the ability to create structs or records, right, where this is a collection of information, and for instance, maybe we define a contact. And so you can see if we had a contact that had a name, an email, and a number, whether that's a phone number or a unique identifier, it can be designated as a parenthesis with a string, and an integer. And then we also have key value pairs. So we have hash maps that we can set up here. And those keys can be any of the primitive types, and the values can be any of the container types or primitive types. And as you can see here in the example, I have a string representing, so maybe this is could be for a game of some sorts. It could be, you know, player 1, and it has an array of integers, which could be maybe the number of power-ups that they have, or their health, or whatever we would choose to put into these values and understand on the other side. And it's really specific to our implementation on this for how you choose to define these. The other piece that's very powerful for AllJoyn is runtime detection. And we can do this through what's called a variant. And this allows the ability to be able to have to focus as a developer to remove the burden of, I need to send a contact over to the other side, and I want to publish some sort of contact list, or I want to publish some sort of variable configuration fields that an end user can configure on my device. But I don't know what, I don't want to publish everything and have it fixed. I want to have flexibility, and I want to limit how much data I send across the wire. So in this example here, I have just an array of variants. And these variants are understood on the other side by the type ID when you pull it out, and you interpret this in your application. You see that you have a variant value, and you ask it, what are you? And you get that type, and then you can assign that internally and either render it on some UI as a string field for input, or an integer, or however you choose in your application. But it's one of the more powerful pieces in combination with introspection. Not only now can I ask an application, or in essence an application running on an embedded device, what are your APIs? But hey, look, you're going to send me some data. I can find out what this data is later in time. I don't have to understand it right now. So the way that you define an AllJoyn interface, and what you'll see in the specifications for the service frameworks, is a definition based on XML markup. And again, an interface isn't XML. It's the way to describe it. It's actually composed, and you can do it inline in your software as well, and you'll see that on the next slides. But what we have is a tag that represents the interface name. And so you say this might be org AllJoyn about. And then you say this is a method, and inside that method, and that should be a closing tag on method, will be the arguments that it will input, whether it takes input arguments and output arguments, and what are those signatures on them. And signals are the same. You designate this is a signal, and here is the name of what's going to be sent so that someone on the other side can register a listener. And then for the arguments, they have a name, a type, and a direction. Now the direction is optional when there's a signal, but required for a method so that we know this is a input parameter or this is a return value that's going to be coming back to me. So I can parse this structure on the other side and set up my my data structure, if it's a variant, to be able to start to accept an array of variants, and then can march through on the return response and parse that data. Just as if you would execute a local API call to a library, only now we're executing in a distributed way across other devices. For a property, we allow the ability to understand whether it has read and write access, and this lets us know that it supports either a get or set method, right? So if it's read, it has a get; if it's write, it has a set; and if it's read-write, it supports both. And we can also take these interfaces, and from an understanding point, you will have a high-level node which gives you the class path hierarchy of where this thing lives in the system. So if you use introspection and you say, give me the bus object and hierarchy that starts with /, which would be everything, you would get back these different node XML structures which define the entire application. And then you would be able to parse that XML and then use the XML through the bus attachment create interfaces from XML API call in which to generate your objects to interact with on the other side. And if I went a little fast on that or you had questions, you can chat them in now, and I'll try to slow down when I get to the next point. And we'll also look through all the chat messages that come in, and we'll answer the questions at the end of the presentation. So looking at an example here of this about feature, and again, this is how we are built into AllJoyn core, discovering objects at the interface level, right? So what pieces they support, as far as what classes and bus objects they've registered and the interfaces on them. You can see here we have that node structure. And then we have the interface name. Now the XML, LNS, and the XSI, those are optional fields for the schema and how the definition is supposed to match up so that you can authenticate it and validate it. It's completely optional. The big piece here is you wouldn't get that from the introspection piece. You just get the AllJoyn tags that we showed on the other slides. And if you wanted to look at the entire specification for what these methods fully mean and understand, you can look at that at the URL there you see at the bottom of the page. But looking at this interface, we can see right away that there's one property. It has a version. So we know, because it's read access, that there'll be a get version. We know that it has two methods that we can invoke, and we know that it's going to be sending some signals. So that's important because we can understand and we can set stuff up on the other side here. So we can generate our object based on this XML alone if we put it into our software, or we can inline build this out, which is straight from the C++ software as you're seeing here, which allows us to create an interface. That's that first part of the code. We first get an interface description. We then assign it, and we tell the bus attachment that we are adding this interface description, right? And here is the name that we want to give it. And then we're going to go ahead here and start adding methods into this interface. And so like we saw before on the other side, we have a get about data. And this has a string, so that the second parameter there on this add method is for the input signature. The second parameter is for the output signature, which we can interpret by understanding the syntax as this will be an array, and it will be a hash, right? It will be a key value pair of a string key and a variant value that we'll be able to introspect at runtime and determine what's been sent over to us, right? Or what's been returned to us. And then the last parameter is our name that we've assigned to this. And this is really, as we saw before here, and I'm going to come back up to the other page, this is what defines the variable name. So much like when you look at a header file for an API and it has a variable name parameter, we can see here there's a language tag and an about data. Well, this software here that you see in the C++ code, if it was introspected, would return that XML that you saw on the previous slide again. So it has to match up, and you want to be a little bit descriptive with your variable names. Now this could be L and it could be A for the return value, or just R, but again, it doesn't provide any hints to someone on the other side that's receiving this. So it's your way as a developer to be friendly and put in something that's meaningful. If someone were to look at this quickly, they would understand, oh, I get back some about data, and I provide to this method the language tag. And then the same thing holds true on a signal. We give it the name of the signal, we give it the arguments that are sent across the wire that we'll be publishing, and we name each of those values here. So with this, we have two shorts. We have an array of a struct which contains an object path and an array of strings, and those strings will be the interfaces on that path. And then we have our optional data, that about data, which is our strings of variants, which we can find out, which contains the make, the model, the manufacturer, the app ID, which is unique, and some other values that are defined in the about feature specification document. So there's a difference between the Java or the C++ implementation and the Java language binding for AllJoyn. And in the Java language binding, we use annotation on an interface. And this allows us to either interpret the types for the reply signature or the input arguments. But as you can see here, on the bus property, we have an annotation. We say this is going to return a short. Now, if we left off that signature in the parens, we, through the process of annotation in the Java language, we can determine that this is a short, and AllJoyn will automatically fill that value in for you. So unless you are using unsigned ints that need to be sent across the wire, or unsigned longs or floats or doubles, we can interpret those types for you, but it's best practice to include them so you get accustomed to writing the signature down so you know what you're sending across the wire. And so again, we just use these annotations of a bus interface, and we say this is going to be org AllJoyn about. Here's the bus property. This is going to be assigned here as a get version. So version is our variable name. That's our property name. We have the two bus methods, and we have the bus signal. And so regardless of the language, we have the ability to set up all these interactions on whatever language binding we choose. Now there's one other piece here that's in the thin client software, and the thin client software is very table driven. So we have a different type of syntax, and what we have here is when you define your interface, the very first entry into this table will be your interface name. And then you start to define your elements, and this is your properties and methods and signals, and all properties are start off with an @ symbol. Right? And so this says this is a property, and the less than and greater than are both the input and output parameters. So a greater than is the output, and so the version is going to return, right? It provides a get method of a short value. Question marks represent bus methods, and exclamation points represent signals. And you can see there on a signal, it's all output parameters. But on that get about data, because there's the less than symbol, it's accepting a string argument, and that's going to be the language value. So in the thin client, we save space by not providing those variable tags, right, for the definitions. And you have the ability at which to use all these same things. So regardless of the language that you're using, you have the tools at which to build your interface by either an XML or using the APIs and definitions within the language binding. So bus methods are really conceptually one-to-one interactions, and they're remote procedure calls. So you create this proxy object. Again, it's kind of like looking in a mirror and the reflection of the actual piece. And you're going to call that method. The AllJoyn framework's going to form that and manipulate it as an AllJoyn message. So it's going to set up some header information. So the proxy object, when you create it, you give it the destination piece, and you'll see that in the software. And it creates this header of the destination with the sender, so your address as the return, so your unique name, because the framework knows that in the application. It sends this message across with the signature and the payload of that signature. It's going to execute that code on the other side. That code function is going to return back your next value, and that's going to pass it back, so your proxy object that you called on, it gives you the value right back. So the big important piece with bus methods is that they are blocking. When you call one, you will get a return response. And so it's important in your software that you understand that it's blocking and you don't make these calls on a UI thread. And it's also important that you avoid making bus method calls within AllJoyn callbacks themselves. So you always want to use all these calls and move them over to a separate thread. So for instance, if these applications here, if the proxy bus object called over to the other side to get some bit of data, and that application 2 over there said, hey, wait, I need to call another device to get more information, right? You're not going to be able to chain those events down the line, because you'll eventually time out for one, and you'll also be chewing up, and you'll have alerted thread errors, where you're trying to make another thread with AllJoyn within an AllJoyn thread. And that really pertains to high-level OS, so you'll start to get those different errors. So it's important that when you receive in App 2 that bus object there that executes for the software, that it returns right away or in a relatively quick time period, so the other side doesn't time out on waiting for a response. And it's important to note, as you'll see here, that there is a timeout value you can set. So by default, I believe it's 60 seconds for the timeout value, I believe, and you can also change that to whatever you choose here. And that's that second argument that we'll get into. So in C++, in order to execute on the other side a method, what we first do is we create the proxy bus object, right? And what we tell it is, here is the bus name, and that's either the well-known name from the previous session that we went over, or the unique name, which is the AllJoyn assigned value to the source code that you've attached to the AllJoyn framework. The path, this is where that source code lives on the other side. So maybe this was a game and it was player A or player B that we want to interact with, right? And then the session ID. And this is important as part of, just like your a letter that you send in the mail, right? This is the absolute address of where things go. It's all the information that makes it up, right? It's who it is that you're sending it to. It's the address of where it's going, and that session ID is really kind of like your zip code in a sense, right? So it's all the things in this grouping should be able to interact with and be invoked. And then what we do is we take that proxy object and we add the interface into it that we're going to be executing with. And then we simply call here a method call, and this is right there in that middle of the screen, and we say call on this interface, this method, with this argument, and stick the response value into that reply message. So that null that you see there, that is the input argument, and that 0 designates the number of arguments that we'll be sending. And if you look at the API definition for method call, I believe there's another argument that you can specify and give the timeout. So you can say timeout after a certain amount of time. And sorry, I said 60 seconds. It's actually 40 seconds for the default timeout. And then we have, once you get this back, AllJoyn will put in through the proxy bus object, it's going to put in the reply, and then we can go ahead and look at the number of arguments and see if there was an error or parse out and actually start to analyze the return value. In Java, it's slightly different, and it may look a little cleaner, and that's because, again, we've been able to annotate things and set it up in a certain way here through the language binding. But what we have here is we have a get proxy bus object. Now, your code probably won't look exactly like this. This is taken straight from the About feature implementation hosted on the get.allseenalliance.org, and so that's why it's set up here into the two methods. But if you can follow the code here, the very first line of what we're doing is grabbing the proxy bus object, and that's down there in the page at the last line here, where we actually call into the bus attachment, and we ask it, just like we did in the C++, we say, here is the name, either the unique name or well-known name, of the application on the other side. Here is the object path where the code lives. Here's the session ID, and here is the array of interfaces, right, that is going to be supported on the other side. And then what we do is we ask the proxy bus object to give us the actual individual interface we want to interact with. So this is that about This is that about interface that we wanted to grab. And then we're going to call the method, just like we did before in the C++ code, only it's a little cleaner in Java. We just call the method on the object itself and assign it to the value that we want. So it makes it really, really clean in how we can go ahead and set this stuff up. And as I've said, you can really consider these interfaces and objects really as remote libraries, and you're just calling methods on them. And AllJoyn does all that heavy lifting of uniquely addressing, moving it over to the other side, doing the data marshalling so it takes that char star and turns it into a Java string, and it manages all that stuff for you. And internally in AllJoyn, all this stuff is happening under the hood with various built-in interfaces that are part of the AllJoyn framework. So there's a ping method that you can actually execute to understand that a device is still present on the other side, and that you actually have something you can talk to before you start to execute your code, or to speed up some awareness if you want to build your own logic for, based on if it's naturally going to time out or not, you can call these built-in methods of AllJoyn. So signals are asynchronous broadcasts of information to everything that is connected on the provided session ID. So that zip code that I kind of referred to a little bit ago as a mailing address, you know, it's the group value. It's what designates that group, and it's a way to execute a method across all of those different applications. And so the big thing here is that signals travel from a bus object, so you need a bus object to send one. So in Java, with the Java language binding, when you build this out, it's a little bit interesting on how you create that, because if you are just a sender side, you still have to register your bus object. And it feels a little interesting when you look at the software, but when you think of it conceptually, is that if signals are emitted from objects because they have to be assigned into a path, it makes total sense. But when you look at the code for the Java language binding side, it looks a little disorienting, because one side is sending and not executing anything incoming, and so you have to see it, and you have to write the software. But if you really think about it conceptually, signals are sent from objects. It makes perfect sense. And in order to receive a signal, you have to have a signal handler and that corresponding object set up. And so that's why you see here on the app on the left, even though it may not be exposing functionality, it must still create that bus object and then register signal handlers on that. And so when that signal comes across, the AllJoyn framework is going to look at the message and say, hey, I have an application that's registered to receive this. Let me pass up the message to that application, and then the signal method will be executed. So looking at the software here on how to send a signal, it's quite similar to what we were doing with the call, and it does look like a lot of code here. Again, I apologize. This is straight from the actual source code. I didn't want to modify this or trim it down. I wanted to provide it so you can actually see this feature in action. And so this whole first part of the software here, the first lines above the last line, is all about setting up the arguments that we're going to send across. So this is setting into that message arg, which is our structure that we use with AllJoyn at which to maintain the information we're sending, right? We're going to set it first based on the signature as a short, which is that Q indicator there, which is going to set for the version. We're going to set another short value, which is the port, so on the other side, what we want somebody to use when they do a join session call. And then we're going to set up the interfaces and build up that mapping of the object path, right? So this is that last line there after that for loop If you can see my cursor right here, it sets the object path with an array of strings. So on each object, we've iterated through and listed the interfaces. So we have a shortcut, so we don't have to introspect every single device to figure out what is interesting. And then we set up these optional values here, these values here as far as the data that we want to be published. So in the spec, it designates that you put in a make, a model, a manufacturer, so that you know what the product is or the application is. And then we simply, from the object, in the bus object, there's a signal call. We call this method. We give it the handler that we set up, and we give it the arguments, and we give it the flags that we want it to be sent with. And this is now going to travel to all applications that are connected. And I apologize for the font here, changing it here on the size, but on the signal here, on the, this is for Java. Sorry, I really apologize for this slide looking the way that it does. This is the Java side on how we send a signal. So what we do is we create what's called a signal emitter. So across all the language bindings, in the Java language binding, the only difference between all the API calls is really around sending signals and creating that interface. Everything else holds true as far as what's exposed on a bus attachment, what's exposed on a proxy bus object, and how those interact. But in Java, if we want to send a signal, we create this signal emitter class. We set some flags on it, and then we get that interface out of it. And then we set up here in the latter part of the code, we create our object descriptions and set everything up, and then we use that emitter object and we call the method that we want to have executed. So this is that announce method, that signal that's part of the definition of this interface. And we're going to send it the version, the port, the object description, and the array of the features per the spec and per the definition of that interface. So moving on, we know what bus methods are, we know what signals are, and now we can look at what properties are. And these properties are conceptually the same thing as a bus method, only they have a defined semantic of get and set. So when they are executed, we call get property, which is a built-in part of the API, and that's going to execute that on the other side as a get property, and it's going to return back via the same way a single return value, which is what that property represents. So again, this is just like building your class in an object-oriented approach, and you're providing public get and set methods to a variable. And the big important piece is that this variable you can attach, because it's part of a session, any application, if it has the ability to set it, can start to manipulate that variable. So maybe I am a device that has volume control, and so I expose volume as a property, and I say you can both get and set the value. And now I've exposed the ability for any of you developers out there to find my interface, see that I have a property that you can manipulate, and then you can go ahead and get the default value and then increment or decrement that value and set it back on my device or whatever it is that I've created. So it provides that whole distributed architecture approach for libraries, all on this local network. So again, with AllJoyn, the whole principle is to find things around you that are interesting and interact with them. So looking at the way this works here with the properties, on the service side, what's built in as part of that bus object is a method you can overload that's just get, right? And what it passes in is the interface name, the property name, and the value. So with this, you have the ability to say, on this interface, for this property, I'm going to now always return back the version of a short, which is 1. This is the first version of the about feature. In the calling side, we do the exact same piece that we did before with calling a bus method, where we create the interface description, we create a proxy object, again, that kind of mirror representation of it, and we give it all the information for the session ID and the path. We add the interface that we want to interact with on the object, and then we call get property that built-in method of a proxy bus object, and we give it the interface and the name, and that's going to go ahead and execute that get on the other side of the device, or the other application. So again, on the Java side of things, all we have to do is we create our method, which is getVersion. We designate it as a bus property, right? And we give it a signature. And then, again, I'm really sorry about the font here on how this translated over. But the version here, we implement a method in which to get or set the value. We create that proxy object, we get the interface, and then we just call the method of getVersion or setVersion. And so it's really clean in the Java language binding. It may look a little bit more like you have to do a couple extra API calls on the C++ side. So now knowing all of these things, knowing how to find something that's interesting, knowing how to connect up to it, knowing how to build these interfaces, we start to get into the really, really fun pieces with AllJoyn, which we call a sessionless signal. And everything you just learned about the about feature, that announce signal, that feature itself, what it's doing is it's advertising the unique address. And in that announcement, as you saw, there was the port so that another application can do a join session. And that join session is going to be set up so that we can then start to execute those bus method calls if we choose to, or it can be leveraged by the objects that you expose into the AllJoyn framework. And the way that we find out about all these pieces is through a sessionless signal. Now, again, a normal signal, as we've talked through here, you advertise your name, you have another side that does a find advertised name and picks that up, and then it sends a join session call and it connects up, that goes through the framework, you have the handshake that occurs through the session port listener, it returns back whether it's accepted, and then you have this connection that will be established and it has a unique session ID to it. Right? And then you go ahead and you have your application, you send it over, and you execute and send this signal on that session ID so that the other applications can receive it. Well, again, with a sessionless signal, your software looks much cleaner, right? You only have a few lines of code to set up, and you get the ability to do exactly this right here. Send that data to everything that has a registered handler. There's no need for you to have to think about who do I connect to? What do I connect to? How do I decide whether I'm advertising, whether I'm discovering? How do I build all that logic? All of the concepts that we've gone through here as far as the core, that's all rolled into one pseudo application in a sense that's part of the router node itself. And this router node has the ability to advertise org_alljoyn.sl for sessionless signal .change ID. And that change ID is always increasing every time there's a new sessionless signal. And the architecture is actually, I believe, going to be changing shortly as a proposal through the AllSeen Alliance. So I would encourage you to, if you're developers out there, participate in the Alliance, join in on the discussions, join in on the mailing list, because you can be involved in the architecture and the direction at which it's going. But today, when you look at the source code, you'll see that in there, in the AllJoyn core, router, sessionless object.cc, that's where the implementation of this occurs. And you'll see that it does a find advertised name for org_alljoyn.sl. And then once it finds that advertised name, it does a join session asynchronous. On that join session asynchronous, it then maintains that session, and it does a handshake of here's my session, my last known change ID that I received. What messages are there for me? Those messages are transmitted over the session, and then the AllJoyn framework, that sessionless object, passes it up into the signal handlers so that any application that's on the network that's interested in, say, receiving about information from the interfaces that we've just discussed will start to receive all those callbacks. Anything that is using the notification service, they will then receive the notifications across the network and be able to interact and show those up on the display. This is how you can build an application on a mobile device or for a TV that can just display messages that are sent from any device out there without having to understand this device is a coffee machine, This device is a door that has a lock on it, right? Or this device is a sensor that's in a refrigerator or so forth. You get the ability to have this dynamic interaction and future-proof your product so that you don't have to worry about all the who joins and who connects and who sends what information. You say, I know this interface. This interface is the notification service framework, and I know that I can receive messages. And I know those messages have a structure of a string, a language value, and you can look at the interface spec, and we can all agree that this is the way that a notification should be and what it should contain. So who it's from, the icon that maybe should be displayed, and various bits of information. And we can now build an application that has meaning today and years to come, because the interface may be extended to add new functionality, but that common set of APIs still exists. And that's a very powerful piece for when you design your products and you build everything out, you'll be able to understand how they all connect at those API levels. So even though in the future things may become deprecated, they'll still exist. And that's why we have in these implementations, if you look at the About feature, the notification, there is that version property. And so you can query that to understand if there's semantic meaning that's changed in the interface specs, or if the one of the sides supports maybe new extended methods that have been added. And that will all be, again, driven through the Alliance, through the Technical Steering Committee. So one of the things to really worry about with a sessionless signal, because the routing nodes themselves are doing all these joins and advertisements on your behalf so that you don't have to worry, it's really designed for small amounts of data. So we don't maintain a session and set it up. So if you wanted to send an image to all the devices that are around you, well, you'd build that through a new service framework, and you'd do it through maybe a raw reliable session, which is a data pipe, or you would use a bus method call or a bus signal to get more reliable communication, so that you send the image maybe in different packets and you get acknowledgement. I received the first 100 bytes of the image. I received the next 100 bytes of the image. And so you can reliably move that to all the devices. So with sessionless signals, because it's built on top of everything that we've gone over with AllJoyn around advertising discovery, and on Wi-Fi, if we just look at that, the advertising discovery piece is using UDP broadcast packets. There is an ability for a packet to be missed, and then that leads to this next piece, that each signal will overwrite the previous one. So when you use sessionless signals, again, it's really about persistent information that's small and meaningful, that can fit into a single signal with AllJoyn, and you can have a max of 2 to the power of 17 bytes in a signal, which is 131,072. But what we recommend, because you can have other variables and strings in there, like if you were sending an image, you'd have your file name, or you'd have other values, we recommend doing it and sending information no more than 110K, right around that area. And if you're curious and want to dive into the source code, those defines and values are all set up in the AllJoyn core project under the AllJoyn core source the includes file message.h. Once you get in through all the different levels of depth, you'll find message.h, and you'll see those pound defines there. And so the other thing, again, is to note, if you're building a product, that each signal overwrites itself. If you are a door, for instance, and you're sending a notification whether you're opened or closed, well, it may be a case where one device, if you did it so frequently at a machine level of open and close, that you would only see the close and you wouldn't see the open message. And that's, again, based on the definition of how we have things set up, where your interface name is what's attached to it on an object path. When you actually join and connect up, and you ask the AllJoyn routing node for the most recent message, it doesn't queue them up in sequence, right? It gives you only the message that makes sense at that time. So there is potential for a message to be missed if you're sending them at such a high frequency. So if you're if you download the notification service and you play with it and you start to see, hey, wait a minute, I'm spamming the messages and I'm only getting 3 on the other side, well, it's because you're creating all these temporary fleeting sessions where you're spinning up TCP connections and they're dropping off very rapidly, and you have potential for, in that small amount of time window, for data to be lost. So how you set something to be a sessionless signal, where you actually have already seen this code already as part of the About feature, and all we did here was set the flag to be a sessionless flag. So in C++, we don't provide a session ID, so that's that second argument here of 0, right? And then we set the flag to be sessionless, and now the AllJoyn core framework, it's going to do what it does and handle this all for you and advertise and connect up and move this data that you want to send over to the other routing nodes, which then makes their way to the applications in the leaf nodes. In the Java side, again, I apologize for the font here, the sessionless signal flag, we set that to true on the emitter, and now when we call the announcement, it will just send it out to whatever is there. If we wanted this to just go to a certain session ID, the signal emitter has a 3-argument constructor, and that middle argument that would be in between the interface and this global broadcast of off would be the session ID. So with that, I want to thank you for listening to all this and kind of recap the things that we've gone through and then open it up for some Q&A. So the application flow that you'll go through, and this is putting all the core concepts together, will be to connect to the bus attachment, set up your different listeners that you have, implement your bus objects that use the AllJoyn interfaces. You're then going to either or advertise, discover, do both at the same time, looking for well-known names, or using the About feature for interfaces that you want to interact with. And then you're going to create sessions. But you don't have to, because you could just leverage sessionless signals by themselves. But under the hood, AllJoyn is going to be creating these sessions for you and moving the data. And then you have your whole application logic of what you've created by going ahead and interacting through all these different ways, by introspection to find out what methods exist on the other side, using the About feature to understand here's an interface that's been published to the AllSeen Alliance, and I know how to call that method. I see it supported. I execute a proxy bus call, and that code executes on the other device, and I've offloaded some computing or to get a return response, or I want to cause some device to turn on or turn off, or whatever comes about. I also want to mention that all the source code that I showed here was all copyright by the AllSeen Alliance, and it's licensed under the IFC open source. So if you open up each of the files by looking at those links, this is the license that you'll see on the top of those files. And so at this point, I again want to thank you for taking the time to listen through here, and I am certain there will be quite a number of questions, and I'd like to open it up for them. So some of you may have been muted during the discussion, so if you could go ahead and hit unmute and ask your question, or feel free to chat it in and we'll answer them right here, right now. So perfect. We've got our first question that's come in. The question is, for sessionless signals, what are the current transports, and how can you send it to all devices that are in proximity? So in order to answer this, just like everything that we've learned about the core, the supported transports are whatever your platform supports as far as the ability. So if this was on Android, this would be over IP traffic, so over Wi-Fi and Wi-Fi Direct, if a Wi-Fi Direct connection was established, or you went into the AllJoyn source code and compiled it with Wi-Fi Direct turned on, or even if your device had AllJoyn running at the OS layer, then you could leverage a Bluetooth connection. So sessionless signals, because they are built on top of the principles of advertising and discovery, it goes over all the transports that are there. As a baseline, IP transport is what would be supported. So if you had all your applications connected up to your home Wi-Fi, and in order to send it to everything in proximity, right, all your applications would have to implement a signal handler that receives the other side so that you can set that up, and then it will travel to everything. So in order to answer your question here on how to send it to everything in proximity, built into it, sessionless signals travel to every single routing node, and as such, the messages will move over, and if there is a registered handler, it will pass up to that application. So, for instance, the About feature, because it is built into AllJoyn core, when you use the SDK, you can start to receive in your application all that information about the devices around you and what their make, their model, their manufacturer, what interfaces they support, and it's how we do the service level discovery. So all you have to do is turn that on, and you'll start to receive sessionless signals from that interface on that signal that's executed. If you have more questions on that, you can chat them in. I'm going to move on to our next question, which is, can I send binary data through the AllJoyn protocol? And yes, you can. You can send and specify an array of bytes, and you can set that up and write it over as single bytes across the wire. You can put that into a signal or a bus method. And if you have a pipe of data, there is a feature in AllJoyn that you can turn on. And it's really about leveraging AllJoyn to get out of the way and give you a file descriptor that you can write and read from on the transports. And it's called a raw session. It's you can set it up when you create your bind session on one side. It's really point-to-point communication, but it is it allows for you to write arbitrary bytes of data and write and read out the other side, and it gives you that raw file descriptor for your Wi-Fi connection or Bluetooth connection or whatever you're leveraging. What I would recommend, though, is that you look at your use case and you look at what you're actually trying to accomplish, and you can benefit from either sending that information in a signal to multiple applications at the same time or using bus methods to push it. If you are curious and want to see this in action, there is actually the open source software that we have around the audio framework, and it's a small building block for audio, and that leverages a multi-point session, and it sends bus method calls to each of the devices, or sorry, it sends signals to each of the directed signals to each of the applications on the session. So hope that answers your question there. If you have further questions on that, you can go to the AllSeenAlliance.org forum page and ask your questions there, and our technical experts will be able to provide you some information. So some people are still a little bit confused, and I probably moved a little too fast on kind of the what is a routing node and what's a leaf node and what's the thin client and the standard client. And so just to explain this again a little bit, so anything that is on a memory-constrained device that doesn't have a lot of processing power, that's maybe running a real-time operating system or a single-loop execution, like maybe it's running MicroCOS or ThreadX or MQX Lite or MQX or any of those real-time operating systems. Those processors don't have enough power to be able to actually route messages to other devices, and they're really designed to be power aware and memory constrained, and you may have other logic that's present. So what's going to happen is they're going to depend on a routing node, which is any AllJoyn application running on a high-level OS, or the software running as a standalone process. So if you write today an AllJoyn application for Android or iOS or Windows RT or your Windows desktop or your Linux desktop, it automatically contains the AllJoyn routing node as part of the process. And your application that you write is really a leaf node in itself to connect to that architecture, right? Only you include the routing node with your process. And so that routing node, all its capabilities and all that it does is it moves messages to other routing nodes in order to move them to an application or that memory-constrained device. And so a thin client has to be a leaf node in the architecture. You can't connect leaf nodes to leaf nodes because they don't know how to move the messages between the other devices. All they know is how to find a routing node, join the routing node, and then ask the routing node for messages that it can look at for itself. So I say, give me a message that's specific for me so that I can execute a method. But you know what? I might want to go to sleep because I'm power constrained and I want to conserve power. So the routing node, because it's on a high-level OS, it's on a better processor, a device with more power, or one that may be always plugged in, it's going to do lots of work on behalf of that thin client device so that it can maintain one TCP connection instead of many to other devices, right? And it can actually go to sleep and conserve power and only wake up when it needs to. If you have further questions on this, I'd recommend you listen to the previous core training 1, and if that was still confusing, go to the alljoyn.org forums and ask them some questions. So we've got another question here that's come in that's asking if there is a real-time streaming service for video and audio. And so I mentioned there was one we have for it's the AllJoyn Audio Service Framework. It's a open source part of an AllJoyn solution. There also is a proprietary solution that Qualcomm Connected Experiences has built on top of AllJoyn, so you can have open source and you can have proprietary solutions. That's the AllPlay solution, and you can get more information by going to the AllSeen Alliance and participating in the technical steering committees and getting involved in order to understand that. Now, there's nothing that's been built, or I believe there'll be a proposal to the Alliance Technical Steering Committee on how to do video correctly, because there are some nuances around that. Anyone there that's ever done distributed video and sending video wirelessly, you have to worry about synchronization with the audio, so lip syncing, frame rates, and all of these things. And so, you know, it's of no benefit for one company to put a stamp and decide this is what audio should be. It should really be a collaboration effort based on multiple inputs and experiences to make sure that it's done properly and that it's done well and that it's done to scale and have a lifetime roadmap. And so really you'll start to see, and I hope you would participate in the Alliance discussions to really try to drive that type of feature. And you'll be seeing proposals through the technical steering committees on video and many other things that many companies are working on. And again, if you have some questions and if you're trying to prototype out anything yourself here around video and audio, you can go to the alljoyn.org forums and ask some help, and we'll provide some suggestions and guidance on how to leverage AllJoyn to accomplish your needs. But there's no limitations with AllJoyn. AllJoyn is a very flexible framework, and it's a matter of getting the interfaces correct. You know, what methods are exposed around video and audio: play, pause, stop, rewind, 10-second rewind. You know, what are all these things that should be part of an interface that makes up a audio or video solution, or a picture solution, or a game solution for a generic board game? You know, all these different types of components. Really, what are the interfaces that make them up, and how do we standardize around that? And that's what the Alliance is driving. So feel free to continue to chat some questions in, or if you want some elaborations on the questions we've asked, I'll stick around here for another 5 or 6 minutes until 7:15. You're also free to unmute and have a conversation in real time with me if you choose. Come on, there's got to be a few other questions. I'm here right now. Let's try to get them asked. Anything, and there are no, you know, anything that's even as simple as what is AllJoyn again. You know, I'm happy to discuss this and rehash these types of questions. And again, I would really like to thank every single one of you for being here, for listening to this presentation, for being involved in the AllJoyn project, and wanting to learn about it and understand it and use the software. It's a remarkable piece once you start using it and you are opened up to being able to interoperate with things that you've never thought are interoperable, and you can discover new pieces of software and really start to leverage things in a whole new way. It's very fun to be a part of the project and write applications that leverage the architecture. All right, I'll give it just a few more minutes here. If people want to start signing off, you're more than welcome to. And again, this presentation was recorded, so it will be posted up to the AllSeen Alliance website. I believe it's on the wiki page. So if you go wiki.allseen.org, you'll be able to click on the training and see the future presentations that we have. Next week, we'll start to cover more of the service framework, so you'll understand what the notification service is, how that functions, our proposal for onboarding, and how you connect a device to your network, how you build a generic controller so that you can start to control anything around you through the process of introspection with AllJoyn, and discovering the interfaces and having a UI layer of hints attached to it, and really dive into those and start to understand how you can use them in your applications, and a little bit, and part of what makes them work as well. All right, so again, like I said, thank you, and feel free to sign off if you choose. I'm going to stick around for another 3 minutes here until 7:15, 2 minutes now. And if you have any questions, again, the alljoyn.org or the allseenalliance.org forums page is the best place to get support and get questions. I'm one of the responders on there, as well as others on the core software team. Yeah, so again, some people still have some questions about routing nodes here, and I just want to put a couple little concrete examples around this. So a routing node really can be an application. So at the Consumer Electronics Show here in Vegas just earlier in January, at the Qualcomm booth, there was some demonstrations that were done around AllJoyn being used on various devices. And so there was an application running on an Android tablet. And these demos will also be shown at Mobile World Congress over in Barcelona in Spain in the next 2 weeks. And what this application was doing is it was showing all the devices that were nearby. And this was really acting as a routing node for an AC unit, for a smart plug, for a sensor that was in a fridge, for all these different products to be able to connect to be able to discover their information, to be able to interact with their controls, and to be able to connect to. So the embedded devices here, they were memory-constrained devices that were on lower processing CPUs. I believe, I don't know all the metrics because they were all done by third parties, but the AllJoyn Thin Client is designed to run on devices with, like the Arduino Do, for instance, which are, I believe, in the order of a very, very simple AllJoyn application, which is the core software. You're looking at about 8K of RAM, and I believe it's about, depending on the service frameworks, you're looking at about 50, 60K of flash, but that's using control panel and everything else. You're using just a very simple interface. It's less than that, but you'd have to play around with it and run it on your platform and figure out those metrics to be exact. But again, these embedded devices, there was a sensor in a refrigerator, there was a chip running in an AC unit, there was a smart plug that was there. So all these things were looking for nodes to connect to. And there was either a TV that was present in the room that could have been used. It doesn't matter from the architecture, it just tries to find one that's running on a high-level OS. And there was also an application on Android running on a tablet. So these devices were connecting up to it, and then they were interacting with, again, other devices that were thin client devices. So a sensor in a refrigerator was interacting with lights, and so it was sending messages that the routing node was passing from one leaf node all the way over to another leaf node that was an application running on a set of lights, and those lights were able to interact with this sensor without the two companies having to work together. They used a common interface, and one set up listening for a signal and one sent a signal. So when the door was open, when the door was closed, and the lights adjusted to that and interacted in a meaningful way. So again, there's another question here that I'll extend my time and answer. AllJoyn is software agnostic, or OS agnostic, being that it is purely software, and it's chipset agnostic. So it can run on other chipsets that anything that's out there that has the minimum requirements, that has enough processing power to be able to move messages. It could be even an 8-bit MCU, for instance, with maybe 10K of RAM or 8K of RAM, or even less than that, depending on the application. That's kind of safe lower limit number, and depending on the amount of flash that's there too. These small little MCUs, like the Arduino, building products based on the Arduino do, for instance, you can start to leverage the architecture and connect up to an Android app or an iOS app or something running on your Windows machine. So it doesn't matter what the chipset is. It doesn't matter whether it's a thin client running on a leaf, basically a leaf node, or it's a high-level application on Android. It doesn't matter what it is at the end of the day, because all that happens with AllJoyn is we pass messages. We pass messages to specific interfaces, as we've just discussed. Those messages in AllJoyn have a structure. They have a definition to them. And so we're able to now interoperate, and everything speaks AllJoyn. So an Android application, for instance, or an iOS application that discovers a leaf node device that's running the thin client, it doesn't see that it's a leaf node. What it sees is an AllJoyn application, and it sees interfaces and methods and signals that it can receive, that it can interact with. So from your application standpoint, everything is just an AllJoyn application. There's no limitations, there's no difference. Everything speaks AllJoyn messages, and everything can communicate through interfaces. So it's a big important piece, because it now doesn't matter what the device is. You can interact with it in a meaningful way based on the interface specification. And so it doesn't matter, again, what the chipset is, and that's one of the big benefits of AllJoyn being part of the Linux Foundation and being an open source project, is anyone can contribute through the rules of the alliance that's been set up and participate in the software development. And it's chipset agnostic, so it can run on any silicon that's capable of supporting the framework and running the instruction set that you can compile to. I hope that answered everyone's questions here. I'll give it just one more minute here, so we end up here on an even number at 7:20. All right, so I again would like to, just at 7:20, I'd like to thank everyone. If you have any further questions, feel free to go to the AllSeen Alliance forum page, ask your questions, and with that, we'll conclude today's session here, and I will stop the recording here. And again, thank you everyone for participating and coming up and taking time from your schedule to listen to these presentations. And I would encourage you to attend next week's session to find out more about the service frameworks and possibly even inspire some inspiration to propose your own service framework to the Alliance. So thank you everyone again.